All right. We're good to get started.
I think so. Okay. Okay. Go ahead.
All right. Well, good morning, everyone, and thank you for joining us today. This is our final episode of our live learning at home 2021 sessions on the topic of Hooke's law and running blades. And in this episode, we're going to be talking about engineering and sports again, and we're going to be learning a lot of really cool things.
Okay. Hi, everyone. If you don't know me already, my name is Alyssa. I'm an engineering outreach program instructor, and I'm also a mechanical engineering student at Ontario Tech University.
And hello, my name is Anna. I am another engineering outreach program instructor, and I'm also a software and biomedical engineering student. So just before we get started in our content, I'm just going to review our code of conduct. This is just a reminder to please join the Zoom session with your first and last name, just so we know who you are and we can call on your name to answer any questions. Please keep your microphones and cameras off, just for your safety and privacy, since we will be live streaming these sessions on our YouTube channel. And again, the chat function should only be used to talk about the activity during the session and to ask or answer any questions. We don't want it to be full of spam, so that we're able to see what everyone has to say. And lastly, just please respect everyone in the virtual classroom, which all of you have been extremely good at doing. And again, all of our live at-home learning sessions are being recorded and live streamed on our YouTube channel. So the focus is going to be on Alyssa and I and the presentation, so you're not required to turn on your camera or your audio, but you can if you would like to. All right, so since it is our final session, I want to ask you guys, what does STEM stand for? And this time it's not on the screen. And it looks like Joshua's on the ball. STEM stands for science. All right, STEM stands for science, technology, engineering, and mathematics. Absolutely. And if anyone wants to add anything about what they know about STEM, they can absolutely do so in the chat. But again, just for review, science is our understanding of the world around us through different experiments. Technology is what we can create from science, and it is the tools and machines that are going to allow us to solve problems. Math is using numbers, shapes, and patterns to understand the world and using different operations. And lastly, when you bring it all together, we get engineering, which is solving our real world issues by designing and building models using science, technology, and math. So just a little bit review, and I'm going to pass it on to Alyssa now.
Awesome. Thanks, Anna. So here's what we're going to be doing today. We are going to be learning about biomed engineering. Does anyone know what that is or has heard of that term before? Biomedical engineering. What do you think biomed engineers do? What do you guys think? So the clue is in the name. So biomed, bio, medical. What does that bring to your mind? What do you think of? You? Are you a biomed engineer, Joshua? What do you think? You know, what do you know, Joshua? Would you like to tell us? Well, when I think about biomed engineering, I think, well, if I split up the word bio, so biology is like the study of like life. If you think about like plants and animals and people, kind of looks at the study of all of those things are living, right? So it's the study of that. And then medical, if I think of like medical, I'm thinking of like doctors and nurses and all those kind of things, like hospitals, and maybe even in like very specific fields like chiropractors or optometrists or there's many different fields that biomed engineering kind of covers. But very similar to regular engineers, they invent and design and build and test and analyze. Ooh, Joshua has an answer. Yes, that's a perfect answer. So Joshua says that biomed engineers study, design, develop, evaluate biological and medical systems and products, such as artificial organs, prosthesis, medical instruments, and information systems. That is a perfect answer. And that is exactly what they do. So basically, biomedical engineers use the same kind of thinking as any type of engineer. They have to invent, design, and build and think outside of the box so that they can tackle real world problems that happen maybe per se like in a hospital or in any situation that has to do with the human body. Okay, so my next question is, do you know any other types of engineering? No problem. Do you know any other types of engineering aside from biomed engineering? Because there's a loads of different types out there. Yep, mechanical is one, chemical is another. Any other ones? Software, for sure. Civil. Yep, management and geotechnical. Wow, that one's new to me. Astronomical, for sure. Yeah, like aerospace. Awesome. So you guys got it. Those are great examples of engineers, and they all of them exist somewhere in the world. So if you want to be an engineer, you have a lot of options. Okay. So this series is all about engineering and sports. There's a lot of applications that engineers use when they look at different types of sports, and not all sports are the same. So we can use different types of thinking depending on what the sport is. So in sports engineering, we try to consider how athletes interact with their equipment and their environment. And we want to make sure that one, they're safe, and two, they can perform to the best of their ability with the equipment that maybe engineers build for them. So in the mechanical kind of line of thinking, it uses a lot of physics and motion so that we can make the sports equipment relatively efficient or very relatively efficient to optimize the design for the athlete so that they can improve their performance, they can get better, and they can train harder. In material science engineering, we pick certain materials so that they can have the best performance. So for example, for a trampoline, perhaps you're probably not going to make the trampoline, the mat that they bounce on, out of metal, because that would hurt. Maybe more so they would use a type of fabric or a piece of plastic so that it can bend more and it's easier on the feet. So something like that. Biomed engineering obviously is a big important aspect of sports because we use our bodies to train and we use our bodies to perform. So we want to see how athletes move around when they do their sport. And how we can accommodate these factors when they move around. So if you're playing badminton, you're moving your arm a lot, you know that maybe if you're adding like a prosthesis, maybe accommodate for that arm because that's what's moving the most. Civil engineering is another one that people don't really think about when we're thinking about sports. So civil engineering is used when we think about the structural needs of the environment that the athletes need to perform in, which is maybe like in a gym, in a gymnasium if you're playing basketball. Maybe it's in a gymnastics gym, which is different than a basketball gymnasium. So we have to think about those things too. Computer engineering is a really cool one that I think also not a lot of people know about in sports. If you've watched the Olympics, you'll see like there's a lot of technology that they use. So for example, when they are looking at photo finishes and they don't know who finished, they use technology to see who finished first so that we can give the medal to the right person. And finally, manufacturing engineering, along with the sports equipment and making it efficient, manufacturing engineering kind of plays with that as well. Okay, So this will probably be familiar for you guys since you have all been to these sessions before. Does anyone know the 5-step process for our engineering design process? Would anyone like to tell me? And you can type it one by one, or you can type the whole thing. Wow, perfect. You're prepared, Joshua. You got it. So first one is identify the problem, which is exactly right. So you got that one right. So we need to identify the problem, because if we don't have a problem, then we can't solve anything. So it's very important that we understand what the problem is before we go in and solve it. Second part is brainstorming ideas. So before we even jump in and make our model or do anything else, we want to brainstorm ideas. We want to write down everything that comes to mind for our problem. Maybe what kind of materials we want to use, maybe how we should build it, maybe what are the types of problems within that problem that we have to solve. Because typically one problem doesn't have just one problem. It's normally a bunch of different problems rolled into one. Okay. Okay. Apologies. So next step is designing a solution. So does anyone know why we have to design a solution? Yes.
I'm sorry, I got kicked out of the meeting.
No worries, Ema.
Because in order to know the actual to know what the actual product is, that what it looks like, you have to design something. Like say you're making like a robot like R2D2, then you need to know what colors, what kind of mechanics that he has in order to move or be.
Exactly, that is a great answer. And no worries for those who are disconnected. I'm not sure why that happened, but I think you guys are all here now. So I will move on. We're glad you came back. And Joshua had a great answer. So yeah, we design a solution because if we don't do that, then we won't know what to model, which is our next step actually. So we want to make sure that when we're designing a solution, we actually physically draw out our design. If it's a physical model that we have to make, we want to choose the colors for which our design is going to have, maybe how we're going to build it. These are the materials we're going to use, and these is how we're going to put it together, that kind of stuff. We're going to have a plan. Making a model is my favorite part. We just have to build what we see on the paper. And then the last step is to test and evaluate. Exactly, Nathan and Jason, you're exactly right. So testing and evaluating is super important, because if we don't do that, then we could be giving a customer a product that could break down, that could not work as we initially wanted to. So we have to make sure that when we test and evaluate it, it works to the outcome that we want. And I think everyone said at the end that we go back and we do it again. If we find that we test it and we realize that there's something that we don't like about it, then we can go back and we can look at one of the steps again and revise it, so that when we test and evaluate it again, then we have a better outcome. Okay, so I think a lot of you were here for the last episode, which was Javelins, and I believe you built one of these for your activity. So recap on Javelins. Javelins are light spears designed to be thrown, as shown in the picture, or as shown in the GIF here. There is I think he's a German, and he's throwing his javelin as far as he can. And as you can see, as it's flying, it's producing, or it's the same as projectile motion. So projectile motion, yeah, exactly. So javelins try to kind of cut through the air so that there's less drag, so that it goes faster. And that's all part of projectile motion. So projectile motion uses a projectile, which is an object that is being launched. In our case, it's the javelin, and it creates a trajectory. So you can see in the next photo, you can see that there is a line. So this red line here is the trajectory, or the path of the object where it's being launched. And you could see where it goes. And typically in projectile motion, it's always about, the arcs, or if you've heard of a parabola before, that's the same shape, kind of an upside down U. Okay, cool. So this time we're actually going to be learning about track sports. So there's a bunch of different types of track sports. If you watch the Olympics, there's many different types of track sports in the realm of track and field. There's sprinting, which is that you can cover short distances from like 100 meters, 200 meters, and then you get longer distances like 400 meters. And then there's also things like 1500 meters, which is quite a bit around the track and it takes a little while, but there's athletes that could do it, which is really cool. Yeah, like Usain Bolt, exactly. Usain Bolt is retired now, but used to run these sprinting races. There's also hurdles. You can see in the next one here, there's these women jumping over these hurdles as they make it to the finish line, which is really cool and something that I could never do because I would probably trip. And then there is a relay, which is probably one of my favorite events. So the relay is essentially you have 4 people, and depending on the relay, it could be like a 200-meter relay, a 400-meter relay, a 100-meter relay. Essentially, the 4 people start at different points on the track, and you pass the baton. Exactly, Nathan and Jason. You pass the baton to your partner, and you make it away across so that all of your teammates touch the baton. Okay, so does anyone know about the Paralympics? I feel like this isn't talked about as much as the Olympics. Does anyone know? Give me a yes or no in the chat if you have heard of the Paralympic Games. Yes, nice. Nathan and Jason. Has anyone else? No, Prafti hasn't heard of it. Joshua's heard of it. Anyone else? I got a few more yeses. Shoria and Rachel both said yes, they know what the Paralympics are, which is really awesome that you know what they are. But for those who don't know, the Paralympics are basically, they're exactly the same as the Olympics. They're an international sports competition for athletes who have physical, mental, or sensorial disabilities. So you technically need to have a disability to compete in the Paralympics. That's why they're for these people. Yes, Joshua, do you have a question?
My theory of like running, like I think that they should not like run like very fast at the start and then go very very fast at the end, because then you could hurt yourself and you would not have the strength to be able to finish. You should like go slow, and then when it's the end you go fast so you could win.
That's a good point. I maybe if it's a longer race, that would make a lot more sense. So if it's like maybe like a 400 or an 800, maybe going faster at the end would make a lot of sense. But I think if you're going 100 meters, which is very, very short, I think like the record's like 8 or 9 seconds, which isn't a lot of time. You could just go all out. But for sure, saving your energy is really, really important when you're running these types of races. But awesome. So there's actually 6 different categories for these Paralympians. You could either be, or a mixture of, an amputee. You have cerebral palsy, an intellectual disability. You're in a wheelchair. You're visually impaired, and les autres. So if you are in one of these 6 categories and you are an athlete, you can most definitely participate in the Paralympic Games. There's quite a few sports. Yeah, exactly, like Terry Fox, but in the Olympics. There's quite a few sports that are covered in the Paralympics, including track and field, like we see here, cycling, swimming, fencing, hockey, skiing. Those are both like cold and winter sports. And they are all quite like modified from what you normally have for the typical Olympic sports. But it's really cool to see these athletes, perform, especially because it's not normally what you get to see. Okay, so Has anyone heard of running blades before? So this still has to do with track. Nice, you guys know what a Hooke fox is. That's awesome. Yes, awesome, cool. So if you've ever watched Paralympians, no, you don't know? That's okay. So if you've ever watched Paralympians run on a track or run races or marathons or whatever type of running event, you've probably seen running blades before. So there is this guy named Van Phillips. And when he was 21 years old, he had his left leg amputated below the knee because he got into an accident. So he was given prosthetic leg, so something similar to what's on the left of the screen, but he was kind of frustrated that it didn't really work like his other leg. And he kind of nicknamed it the dumb leg because it was pretty heavy and it wouldn't allow him to run and jump like he was able to before he had to get his leg amputated. So being a biomed engineer, he decided, hey, why don't I do something different? Why don't I design a leg that would allow him to bounce and jump and run? So after many, many years of designing and making and testing and probably breaking a lot of those prototypes that he made, he eventually got to this prosthetic leg that allowed him to run. And you can see he's wearing something like that. And it's very different than the normal prosthetic leg that you would wear. And we call these running blades. Okay, so we're going to talk also about elastic potential energy. And I'll tell you why it's related to prosthetic legs and running blades, because it does, but right now it may not look that way as of yet. So elastic potential energy is stored energy associated with an object that can stretch or compress. So a good example of this is, let's use our trampoline example. If you're bouncing on a trampoline, yeah, exactly, a rubber band trampoline, a lot of things that can stretch or compress, those all go through elastic potential energy. Let's take the rubber band example as a good example, because it was mentioned. So when I stretch a rubber band and then I let it go, it'll snap back to its original position. If when I'm stretching the elastic band, it will increase the elastic potential energy, and then letting it go converts it into kinetic energy. And then obviously it snaps back into its original form. But if I keep on stretching that rubber band until it breaks, then it will have the maximum elastic potential energy before it can not take it any longer, and then it breaks. Or if we think about jumping on the trampoline, our legs kind of load up before we push off, and then we jump up and down. So that's another example of elastic potential energy. Exactly, I see some awesome examples in the chat. Okay, so has anyone heard of Hooke's law? Is that a familiar concept? Yes, ooh, nice. No, that's okay. Yes, okay, it sounds like a few people have heard of Hooke's law. And no, if you haven't heard about it, that is totally fine. And I will explain it to you. So Hooke's law is the amount an elastic material changes when it is compressed or extended and is directly proportional to the force applied to it. So that's a lot of words. So let me break it down. So the first part says it's the amount an elastic material changes when it is compressed or extended. So let's take our example here with the spring. So we could see that our spring is being extended, it's being pulled down by a weight. And you could see that it's obviously going through some changes. We could see an extension, it's getting longer, but it's also gaining a lot of elastic potential energy, right? If we pull it even further, it's going to gain even more. Kind of similar to the way that our legs work when we're jumping on the trampoline, or that rubber band example. So there is a formula for this. We're not actually going to use our formula today, but it's really good to know if you're going to use this for future calculations. So the second part of this definition is directly proportional to the force applied to it. So what it's saying is when we apply a force, so for example, if we're putting those weights on the end and gravity's pulling it down, which is a force, as we learned earlier, it will make a difference in the extension. So we can see that it gets longer. And the spring constant is also comes into play. So for example, if we take a rubber band that stretches very easily versus a very, very solid, very heavy spring that is made out of metal, the spring constant or the stiffness is going to be much stiffer for that metal spring than that rubber band. So that's also something that we have to take into account, because obviously if we put the same amount of weight on the end of our rubber band or our metal spring, they won't react the same. Okay, cool. So we were talking about elastic potential energy. This is how we can use Hooke's law along with elastic potential energy. So there's another equation. Again, you don't really need to know it, but if you do, that is great. So you could see in this equation, there is still the extension and the spring constant, but we also have the elastic potential energy, and we have 1/2. That is basically how we create our elastic potential energy, or we can calculate it. So again, you could see that in this example, very similar to the other example, it's just the spring is going horizontal instead of vertical, but we still have some force at the end that is pulling it. And then when we let go, then it turns into kinetic energy. But while we're pulling it, it's going to create that elastic potential energy. And the more we pull it, the more elastic potential energy we have. Okay, let's go back to running blade design. And this is how we'll connect the elastic potential energy to running blades. So typically when we want to design running blades, or when Van Phillips designed his running blade, he had these kind of attributes that he wanted to include. So he wanted it to be lighter than his current prosthetic legs, because he found that when he was running with the regular ones, they were very difficult to carry around or to lug around. And it doesn't really act like a normal leg, because normally you don't really think about lugging your legs around. But if it's heavier than what you're normally used to, then obviously you're going to have some problems. So first thing is it should be lighter than his current prosthetic legs. Second thing is resist forces exerted by the user. So if I'm running and maybe I'm pushing really hard on my feet should be able to kind of push back and allow me to run faster, or give me the power I need to push off every single time I step on the floor. So we have to make sure that when we're designing running blades, that they have to resist the forces that we put on those blades. And then finally, as we're talking about elastic potential energy, it's really important that they are able to store that energy and then kind of release it when we need it and turn it into kinetic energy when we're running. So what's really cool about this design is they took the inspiration from cheetah's legs. And you can kind of see the similarity between kind of like the arc. You could see that the arc is kind of, it's pointing away from the way that the cheetah is running. And that's the same with the running blades. Does anyone know why they would take inspiration from cheetahs? Because it's a very specific animal. Like, why not take it from giraffes? I don't know. Why not take it from monkeys? Yeah, exactly. They're the fastest land animal for sure. So, yes. Profik, do you have another answer?
No, it was the same answer.
Okay, no worries. Good job. And you guys are exactly right. So the reason why they take it from the cheetah is they are the fastest mammal or animal in the world. So it's only reasonable for us to design something that is used for running based on the fastest animal, right? Because if we want to be super fast, then there's probably a reason why cheetahs are super fast. And that's partly because of their legs. Okay. So along with the running blade design, I'll talk a little bit more about it. So there is the blade that is probably the most important part of the design. There's two parts to it. I'd say the blade is one of the most important parts. So typically it's made out of carbon fiber, so it's really, really strong, but it's very, very light. Yes, Joshua.
Actually, Like at the bottom, it looks like a piece of tire.
It looks like a tire. It kind of does. You're right. I'd say it's very similar also to if you look at your shoes. If you have running shoes and you look at the bottom, they kind of act very similarly. So you can see that they have these kind of ridges on the bottom, so that when they're running, yeah, exactly, not to slip, so they can grip the ground, and then they can keep running. So good observation.
That's why cars can like go up hills.
Yeah, exactly, for sure. Very similar to cars, very similar to your running shoes. All of those do the exact same thing, and that's why they have ridges. So you're rarely ever going to see shoes with flat bottoms, and that is why. So we need to grip the ground with those. So part of also in the blade, we were talking about it being made of carbon fiber, and carbon fiber are basically these little strands that are very, like, they're a lot thinner than hair, and they kind of like, they twist them together and they kind of like weave them together so that they're very, very strong, and they're stronger than steel. So what they like to do is, depending on the athlete, let's say they're a larger athlete, they will need larger blades. So they will need more layers of carbon fiber so that it can support them, and give them the elastic potential energy they need to push off and to get their power when they run. Another example is if you are running for, or if you want more power in your step, you could also ask for larger blades, because that will also help you get more power as you walk. It's very similar to how larger athletes need more power to push themselves off. And then the final example is if you're a long distance runner, if you're running 800 meters, if you're running even maybe 400 meters, if you're running, let's say, like 1,000 kilometers, which is like a lot of ground. That's around 348,000 steps. That's about 1,000 kilometers you're running. You might want a lighter blade so that you don't have to lug around your foot the whole time. Okay, and then the other part of the design, which is also really, really important, is the socket. So the socket is what attaches the leg or the amputation to the prosthetic. So this actually is quite important. I don't think people think about it a lot. I think people think about blade more so than the socket, but it's really important because it actually controls the power and the force and the pressure that these athletes use to run. Also, they need to be designed to fit the athlete. If it exactly like a ball and socket joint, kind of like your arm. If you think of your arm that's connected to your shoulder, that's a ball and socket joint. So very similarly to your knee, to your thigh and your lower leg, you need to connect them together somehow. So what's really important about this aspect of the design is that it needs to be designed to fit the user properly. If it's not customized to fit the limb, then the athlete might be uncomfortable. Also, for whatever reason, it might fall off, so then they can't even complete the race, or even the blade design might be damaged in the process too. So that's really important that it has to be fit. It has to be safe for the user before we even get to use it. So that's really important. And now finally, you could see it in action. This is what one of many versions of a running blade looks like. You can see that there are lots of layers on the bottom like we were talking about. And you could see that as this person pushes off with their amputated leg, you can see that it's very hard to see, but you can see that it's kind of compressing and it's kind of building up that elastic potential energy. And then as they step off, they can step forward with the next leg because they have enough power to do so. So I think this is really cool. And actually today you're going to build one for yourself. Oops. Okay, and I will hand it off to Anna to show you how to do that.
All right, so thank you, Alyssa. As she said, now we are going to begin to create our own running blades. And our first step, as always, is to first identify the problem. So our mission is to help the Olympic athlete design their running blade for a sprint race. Now our next step is to brainstorm ideas, and right after this, I'm going to let you guys grab your supplies. But first, we want to begin asking ourselves some questions and thinking about them. So, what do you think the athlete needs if they're doing a sprint? Well, they're definitely going to need a running blade that's going to make them go really fast, especially because it's a sprint, so that's going to be a shorter distance run. We want to think about how that's going to affect our weight and how it's going to affect our elastic potential energy. And next, can you make any of your designs with the materials that you have at home? So these are just some ideas of the supplies that you're going to be needing. I have all of these here with me, but if you have any other ideas of things that you might want to add later on, you can look for different materials. But for now, everyone can go.
I don't have some of the materials.
Okay, Ema, what are you missing? Ema, what materials do you not have?
I don't have a ruler, I don't have beads, and I don't have wooden sticks.
Okay, you actually don't need those three materials to make our running blades today. Those are just additional materials, but it is okay for now if you don't have those materials. I can show you what to do if you don't have beads, okay?
Okay.
All right, so I'm just gonna give everyone a couple of moments to grab their materials, and once you have, just type a done in the chat so I know we're ready to move on. Prapti, do you have a question?
Yes. What do I do for a substitute if I don't have cardboard?
If you don't have cardboard, maybe you could ask your parents if you have anything in the recycling that you could use. If you have like an old tissue box, or if you have a piece of Bristol board or a harder material, you could use that too.
Okay.
All right. So again, once you have all your materials, just type done in the chat, and then we can get moving on. Rachel's done. Awesome. Nathan and Jason ask, can prosthetic legs allow people to do backflips? Yeah, I think they probably could. I'll give everyone a couple more moments to type done once they have retrieved their materials. But the big ones that we're going to be needing today are the cardboard, the tinfoil, scissors, and tape. The rest.
Oh, and I don't have cardboard. I just have one small box.
You only have one small box, that's fine. If you're able to find a cereal box or something like that, that's what I'm using. And that's gonna.
I can check.
All right, sounds good. And this is just a reminder, just to be respectful of everyone in our virtual classroom. Just as you would in a regular classroom, please be respectful. Thank you. The main items are some sort of cardboard, tinfoil, tape, and scissors. So our cardboard is going to be the base of our running blades because that's going to form our socket. And we're going to be using the tinfoil for the actual curved blade section. We're going to attach everything together with tape or glue, but I recommend tape for this one. And
No, I don't have a cereal box.
you don't have a cereal box? Okay. Well, if you do have a small box, you can use that as well.
I have one like that big.
Okay, that should be fine. We don't need to make them full size today. That's why we're making a model first. All right, I'll give everyone 1 or 2 more minutes. Joshua, you got a shoe box. Awesome. Prapti, do you have a question?
Yes. So how are we gonna test and evaluate it?
We're going to be putting a little bit of pressure on it. We won't necessarily actually be testing it as an Olympic athlete would, but we're just going to press down on it to see if they can support some weight and see if we can get some of that elastic potential energy working.
Okay.
Nathan and Jason? Can we use aluminum foil instead? Yes, tin foil and aluminum foil are the same thing. Technically, tin and aluminum are not the same elements, but in our case, they are the same thing. They are solid elements for sure. All right, I think I'm going to get us started now. And I'll be moving slowly, so if you don't have everything yet, do not worry. Before we begin creating stuff, we want to think about designing our solution and planning things out. So we want to ask a bunch of questions throughout our entire engineering design process. So firstly, we need to think about how large the socket is going to be. And if we don't have a box that's big enough, we don't have to make a full-sized one. But if we were to design an actual running blade, we want to talk with whoever we're creating a running blade for and customize it to fit their needs and their leg shape. Are we creating one for us? Really? Yes, sort of. We're just going to create one for us. And we're not going to be able to actually wear it, but yeah, so this measurement process is more for an in real life situation where you have a customer who needs a running blade. But we can still ask these questions when we're planning out our designs. So nextly, next, how will we provide traction on the blade? So we want to make sure that our blade doesn't slip when we're running. So we want to think about what the texture and the shape of our blade is going to look like so that we can do that. And the next question is, how long and wide and thick should the blade be? So we want to think about all of the dimensions of our blade before we begin to make it. And yes, Joshua, it is a model, so it's not going to be full-sized or made out of all the proper materials like carbon fiber. This is just a bit of a prototype, so we have an idea of what our running blade is going to look like. And lastly, how will you connect the socket and the blade? So we want to think about different materials that we're going to use to connect everything together. All right, so Nathan and Jason, tape will be good to wrap around the socket and blade. Yeah, probably. That's what I'm going to use today. So our first step is going to be making our socket. And so I chose a very thin and flexible type of cardboard in order to do this. But if you have a thicker one, that is fine as well. So I'm first going to make a socket by rolling this material into a cylindrical shape. So I'm going to cut it so that I only have one side of the cereal box. Joshua, do you have a question?
How do you cut a shoebox?
You might want to disassemble it a bit first. So what I did was I unfolded my cereal box to make it a little bit easier.
Yeah, they wrap it in a certain way, so.
Yeah, exactly.
And then I would just get the bottom of it.
Yeah, you can use the bottom of it for sure. So I'm just gonna cut out this one side, so I have one big flat sheet to work with. And I'm gonna curve it around like this. I'll have it inside out just so we don't have the cereal logo on the outside. And I'm gonna cut off a couple of these flaps. Nathan and Jason, do you have a question? Are there a few pictures to view? No, there aren't. But Alyssa, could you maybe spotlight me?
Give me 1 second.
All right. Perfect. So if you, there's a little bar that you can move to the side to make my video a little bit bigger, and you can follow along and see. Does that help, Nathan and Jason?
Go to pin screen.
So once you cut out your cereal box and you have a flat sheet of cardboard that you can work with, I want you to roll it into a cylinder shape, sort of like this. And that's going to be our socket for the leg. So our leg is going to go in here, just like the ball and socket joints we were talking about. And this is going to wrap around the leg. So we want to tape this shut now. Okay. So now that I've taped my cylinder shut, we have the base for our socket. It's a little messy. So we want to close the bottom of it. So I'm going to cut out a circle that's about the size of the cylinder here, and I'm going to tape that to the bottom. So we sort of have like a cup. I'm going to take the rest of my cardboard and I'm going to cut out a circle now.
Yes, Prafti, do you have a question?
How do you make the cylinder?
Oh, I just took a big sheet of cardboard and I rolled it up. And then I used some tape to secure it into our cylinder shape.
Okay.
Yeah, thank you, Alyssa. Sorry, I can't see any of the hands raised when I'm being spotlighted.
No problem. I will let you know.
Okay, thank you. So it's a little big, so I'm going to trim it.
If everyone wants the picture of the real running blade as reference, I can show you that because I know a lot of people are asking for images. We don't have any images of the activity, but we do have images of the real thing. So if you would like that, just let me know and I can definitely show that on the screen instead.
For sure. On the actual running blade, there was a section in the first picture called the pylon, I believe, and that's an extended section of it that makes it a little bit longer. I'm not going to be adding one of those to mine, but you can add it to yours if you like. Yeah, in picture A here, it says the pylon, and that's a straight section that's going to make it a little bit longer, and that just depends on, you know, how the customer wants their prosthetic to fit. So yeah, that's an option if you want to add another section of length to this, but I'm just gonna directly connect the curved prosthesis part to the socket. Okay, so I've secured the circle to the bottom of my cylinder, and this is going to be the socket. So this is where the leg is going to sit. So next, we want to reinforce the socket, and this is when we can use our wooden sticks. So if you have any wooden popsicle sticks, you can tape them around the socket just to make it a little bit more sturdy. I'm just going to grab a couple of them right now. I'm going to use a long strip of tape, and I'm going to sort of place my popsicle sticks all along the strip of tape and then wrap it around my socket. And this step, you don't have to do the exact same as me. If you have any other materials that are going to work to help reinforce your socket, you can go ahead and use those as well. This is just a bit of an idea of how you can make it a little stronger.
Can you please show us what you do?
I'll show you what I'm doing right now. So I have a long strip of masking tape. And I'm just attaching popsicle sticks to it so that when I wrap this masking tape around the socket, it's going to help reinforce it and make it a little bit stronger. All right, so I'm just wrapping this tape all the way around my, it's a little bit tricky. You can lay the socket down onto the popsicle sticks if that helps you roll it up better. All right, so this has helped to reinforce it a little bit, make it a little bit stronger. And that's using a little bit of our material science engineering that we looked at previously, just to make it molds to the shape of the leg a little bit better. So if you weren't able to do that step, that's totally fine. You can go back and add this later on. And we're going to move on to the next part now. So now we want to begin creating our blade. It's going to come from the bottom of the socket. So I want you to grab your aluminum foil or your tin foil, and I want you to create a C shape using by sort of crumpling it all together and shaping it to how you want. Careful with the sharp edge of the aluminum foil. So I'm going to take it. All right, it's a little loud. I'm going to take it and I'm going to try to crumple it into like that C shape that we saw that imitates the leg shape of a cheetah. Something like this. All right, and since aluminum foil is very easily deformed, you can begin to smooth it out and shape it to however you want. And during this stage, you could even attach that pylon that we saw, that little extra vertical segment that's going to connect our running blades together. So once you've created this C shape or U shape, whatever you want to call it, we can attach it to our socket right under here. And I'm going to be using tape for this. All right, I'm gonna add a little bit more tape to reinforce it just because it's a little bit heavy. And let me just see that's going to stay on. Awesome. So now we've got our socket and the C-shaped part of the prosthetic. We can add cardboard to be cut in the shape of a U to fill some of the space in between, but I'm just going to leave it how it is here. And the last step that I'm going to be doing is I'm going to add some beads to the bottom to increase, the beads or any other material can be used as spikes for the bottom of the blade for support. So we were talking about like traction and how the base of our prosthetic kind of looks like the bottom of a shoe or like tire tracks. So we can add some beads to the bottom to do that. So I'm gonna roll my tape so that it's sort of gonna be sticky on both sides, and I'll show you how to do that. If we make our tape sticky on both sides by rolling it up like this, we can stick one side to the bottom of that aluminum foil, and the other side we can stick our beads on. And if you don't have beads, you can cut out strips of either cardboard, or you can break some popsicle sticks and line them up. We just want to increase the amount of friction and traction that we can get from the bottom of our running blades. So I've created this sort of like tape loop, and that's going to allow me to stick beads onto the side of it. Oh. It's not super sticky, so if they're not sticking quite right, we can add another layer of tape over top. Sort of help us out with that. And yes, if you have any old pasta lying around, that could work too. For sure. Or you could line up some toothpicks. There's a ton of different alternatives and ideas that you could use. And that's the best part about creating a model, is that we don't have to make everything perfect, and we can always come up with better ideas and change things. Oops. All right, so I've attached a couple beads, and I'm just going to add an extra layer of tape on top to secure them. It's still going to be pretty bumpy, so it's still going to have the same effect as if I were to just leave the beads there, but I think they're going to fall off if I don't add an extra layer of tape. So I'm just going to cover them with some tape and press down so they still have that bumpy shape. All right, and this is going to be the base for our running blades, and you can go ahead and add other things to reinforce it. So you can take your plastic wrap that you have before, and you can wrap it around everything to secure it all together, because I know the tape isn't totally secure. But yeah, once you're finished with reinforcing it with some wooden sticks and adding those beads or any other material at the bottom to increase that traction and create a little bit of texture, you can wrap the whole thing in plastic wrap, and then you will have a completed running blade. And I believe that takes us to the end of our session. So I'd like to thank all of you guys for coming to this week's live at home learning sessions. Oh yeah, once you're finished creating your running blades and everything, you can begin to test it by pressing down and seeing how much weight that it can hold and what the flexibility is. And you can make any changes that you want afterwards. But thank you everyone for coming and for participating in all the activities this week. We hope you had a great time. If you want to go back and look at any, it is currently still being live streamed, I think. But if you want to go back and look at any of the steps, you can hop onto the Engineering Outreach YouTube channel